Hi, this video is aimed at AS level students who are studying for the computing qualification with AQA. The idea is I'm going to run through some examples of simplifying Boolean expressions by applying identities and laws. These should match typical kind of exam questions that you might get. I'll begin though with revising some of the identities and Boolean algebra that we're going to need in order to do this.
Okay, we're just going to look at some popular identities that you can use when you're doing some simplifications of Boolean algebra. Let's start with this. If we had the expression A, ANDed with A somewhere, well, let's consider what that really means. We've got an A here and an AND gate here. What's going to be coming out? Well, we've got a 0 here. Going into a 0 and a 0 going there, we're going to get a 0 coming out, and if we had a 1 going in, a 1 and a 1, we get a 1 coming out. So basically the output follows A, so we can say that A ANDed with A is the same as A. Next one to consider is, imagine we had something that said double knotting of something. Well, consider what that is this time. We've got a NOT gate effectively followed by a NOT gate. So if we feed a 0 in here, we're going to go 1 here, then we get a 0 here. Therefore, these are the same. And if we did a 1 in here, we get a 0 here and a 1 in out. So those are the same. So we can say that A, or anything double knotted, is the equivalent of not having the double knots there. Similarly, we can say if we had an A and it was ANDed with a 1, okay, well that would mean that we've got a 1 going in and the A in an AND gate here. If A is a 0, we get a 0 out, 0 and 1. However, if A was a 1, we'll get a 1 out, proving that A ANDed with A is just equal to A. Okay, this is one of the identities that you should really know, but let's prove that the A ORed with an A and B is actually equal to A. Okay, well let's consider the case if A was a 1 here, or a 1 here, so regardless of the value of B, we're going to get a 1 here. Now let's consider though if A was a 0, we're going to get a 0 here, so we'd need a 1 to be coming out here. However, as this is an AND gate, we're never going to get a 1 coming out of here. Therefore we can say that A ORed with A and B is the same as A. Similarly, we should know that the identity where A ANDed with A or B is also equal to A. Let's prove this time with a truth table. Well, A ORed with B would give us 0, 1, 1, 1. Now if we AND the A or B with A, we have a 0, 0, 1, 1. And once again we can prove that this is equal to this, as these columns are the same. Okay, probably one of the most useful theorems here for simplifying Boolean expressions is De Morgan's. It allows us to change the sign of an expression. So for example, if we had A or B, but we noticed we wanted this to actually be expressed using AND gates to help us with simplification of a larger expression. What we can do is we can follow the 3 simple rules, and we're just revising this, I'm not trying to teach you it, but essentially we change the sign and we knot the individual terms and we knot the lot, and those 2 things were the equivalent. And it doesn't really matter what the expression is we kind of got underneath here, we can kind of do the same thing. So follow the same three rules again. We can not the individual terms, we can not the lot, and we can change the sign, and those would be the equivalent to each other.
Okay, this is an example of us going to do a Boolean simplification using De Morgan's theorem. In this case, we're going to turn the OR gate into an AND gate. So we can change the sign as long as we then not the individual terms and not the lot. Notice how this applied to all of the right-hand side. Now, due to the double knots being able to be simplified, we have this, and the identity A and A is the same as A, simplifying to A and B.
So in this next example, once again, we're going to apply De Morgan's law to this. And we could also, again, we could either apply it at this point here for this expression to change this to be an and try and do simplification that way. Or we could apply it, assuming that this is, treating this as one expression, this is the other, and changing the and there. Now, sometimes it's a case of you have to try this and see what happens, and you may come to a dead end where the expression just doesn't seem to get any simpler, and you'd have to go back and try the other way. But I've got a kind of gut feeling here that if I was to apply De Morgan's on the AND operator here, and not the individual terms, it's going to allow me to simplify this side of the expression a little bit more. So let's give that a try. So we're going to, keeping this part the same, we're going to change the sign, and we're going to not the individual terms. We already had the not from there, and we'll not the lot. So we just applied De Morgan's there. And straight away you can see that that allows us to simplify this quite a bit due to the double knotting to become the not of A, ORed with B, ORed with the not of A. Now the not of A, or ORed with the not of A, is simply going to equal the not of A. Therefore this then finally becomes the not of A ORed with B. So we can say that Q is equal to the not of A ORed with B. Let's recap what we've just done there. We've used De Morgan's law to change the sign here, and we've used the identities to get rid of the double knotting here. We've used the identity that the OR of the not of A is equal to the not of A to simplify this expression. So we've got one final example we're going to look at now. We won't need De Morgan's law for this one. The associative law told us that A ORed with B is the same as B ORed with A. So effectively we can move any of these around to where we'd like them to possibly kind of be. So if we group together the A ORed with the not of A, and we'd have the B ORed with the not of B. These two are still the same. The tautology law, the one that we looked at earlier when we were looking at the identities, told us that something that is ORed with the not of something, okay, so A ORed with the not of A, would simplify to being a 1. Okay, we kind of look at that as a gate. If we've got the not of something, if it's a 0, it's going to be a 1 on the other side, a 1, it's going to be a 0, and it's an OR gate, so we're always going to get something out here. Therefore, we can say that Q actually now becomes 1 ORed with 1, and obviously Q now is actually going to simplify all the way down to 1.